Graphics. This includes specification of parameters of application-defined shader, programs performing transformation, lighting, texturing, and shading operations, as well as built-in functionality such as anti-aliasing and texture filtering. It does not provide a means for describing or modeling complex geometric objects. Another way to describe this situation is to say that the GL provides mechanisms to describe how complex geometric objects are to be rendered rather than mechanisms to describe the complex objects themselves. The model for interpretation of GL commands is client-server. That is, a program, the client, issues commands, and these commands are interpreted and processed by the GL, the server. A server may maintain a number of GL contexts, each of which is an encapsulation of current GL state. A client may choose to connect to any one of these contexts. Issuing GL commands when the program is not connected to a context results in undefined behavior. The GL interacts with two classes of frame buffers, window system provided frame buffers and application created frame buffers. There is always one window system provided frame buffer, while application created frame buffers can be created as desired. These two types of frame buffer are distinguished primarily by the interface for configuring and managing their state. The effects of GL commands on the window system provided frame buffer are ultimately controlled by the window system that allocates frame buffer resources. It is the window system that determines which portions of this frame buffer the GL may access at any given time, and that communicates to the GL how those portions are structured. Therefore, there are no GL commands to configure the window system provided frame buffer or initialize the GL. Similarly, display of frame buffer contents on a monitor or LCD panel, including the transformation of individual frame buffer values by such techniques as gamma correction, is not addressed by the GL. Frame buffer configuration occurs outside of the GL in conjunction with the window system. The initialization of a GL context occurs when the window system allocates a window for GL rendering. The EGL API defines a portable mechanism for creating GL contexts and windows for rendering into, which may be used in conjunction with different native platform window systems. Version 2.0.25, November 2, 2010. 2.1. OpenGL Fundamentals 6. The initialization of a GL context itself occurs when the window system allocates a window for GL rendering and is influenced by the state of the window system provided frame buffer. The GL is designed to be run on a range of graphics platforms with varying graphics capabilities and performance. To accommodate this variety, we specify ideal behavior instead of actual behavior for certain GL operations. In cases where deviation from the ideal is allowed, we also specify the rules that an implementation must obey if it is to approximate the ideal behavior usefully. This allowed variation in GL behavior implies that two distinct GL implementations may not agree pixel for pixel when presented with the same input, even when run on identity cal frame buffer configurations. Finally, command names, constants, and types are prefixed in the GL by GL, and GL, respectively in C, to reduce name clashes with other packages. The prefixes are omitted in this document for clarity. 2.1.1 Numeric computation. The GL must perform a number of numeric computations during the course of its operation. Implementations will normally perform computations in floating point and must meet the range and precision requirements defined under floating point computation below. These requirements only apply to computations performed in GL operations outside of vertex and fragment execution. See sections 2.10 and 3.8, such as text, Touré image specification and per fragment operations. Range and precision requirements during shader execution differ and are as specified by the OpenGL SHAD. In language specification, floating point computation, we do not specify how floating point numbers are to be represented or how operations on them are to be performed. We require simply that numbers floating point parts contain enough bits, and that their exponent fields are large enough so that individual results of floating point operations are accurate to about 1 part in 105. The maximum representable magnitude for floating point values must be at least 232. X 0 equals 0, x equals 0, 1, x equals x, 1 equals x plus 0 equals 0 plus x equals x, 0 0 equals 1. Occasionally further requirements will be specified. Most single precision floating point formats meet these requirements. Any representable floating point value is legal as input to a GL command that requires floating point data. the result of providing a value that is not a floating. Version 2.0.25, November 2, 2010. 2.1. OpenGL Fundamentals 7. Point number to such a command is unspecified, but must not lead to GL interrupt, Cheyenne or termination. In IEEE arithmetic, for example, providing a -0 or a denormalized number to a GL command yields predictable results, while providing a nan or an infinity yields unspecified results. The identities specified above do not hold if the value of xi is not a floating point number. Fixed point computation. Vertex attributes may be specified using a 32-bit 2's complement signed representation with 16 bits to the right of the binary point, fraction bits. General requirements. Some calculations require division. In such cases, including implied divisions required by vector normalizations, a division by 0 produces an unspecified result but must not lead to GL interruption or termination. 2.1.2 Data conversions. When generic vertex attributes and pixel color or depth components are represented as integers, they are often, but not always, considered to be normalized. Normalized integer values are treated specially when being converted to and from floating point values. In the remainder of this section, when an integer type defined in Table 2.2 is being discussed, denotes the minimum required bit width of the integer type as defined in the table. The formulas for conversion to and from unsigned integers also apply to pixel components packed into unsigned integers. See section 3.6.2. But bin these cases is defined by the specific packed pixel format and component being converted. All the conversions described below are performed as defined, even if the implemented range of an integer data type is greater than the minimum required range. Conversion from integer to floating point. Normalized unsigned integers represent numbers in the range 0, 1. The conversion from a normalized unsigned integer CT, the corresponding floating point f is defined as CF equals 2b, -1. Normalized signed integers represent numbers in the range -1, 1. The conversion from a normalized signed integer CT, the corresponding floating point f is version 2.0.25, November 2, 2010. 2.2. GL state 8. Defined as 2c plus 1. F equals 2b, -1. Conversion from floating point to integer. The conversion from a floating point value f to the corresponding normalized signed integer is defined by first clamping f to the range 0, 1, then computing f equals fx2b, -1. Phi is then cast to an unsigned integer value with exactly bits of precision. The conversion from a floating point value f to the corresponding normalized signed integer is defined by first clamping f to the range -1, 1, then computing fx2b, f -1, -1, 2. Phi is then cast to a signed integer value with exactly bits of precision. Conversion from floating point to frame buffer fixed point. When floating point values are to be written to the fixed point color or depth buffers, they must initially lie in 0, 1. Values are converted by rounding to nearest to a fixed point value with m bits, where m is the number of bits allocated to the corresponding r, g, b, a, or depth buffer component. We assume that the fixed point representation used represents each value k to m, -1, where k0, 1.2m, -1 as keg. 1.0 is represented in binary as a string of all ones must be at least as large as the number of bits in the corresponding component of the frame buffer, must be at least 2 for a if the frame buffer does not contain an a component, or if there is only one bit of a in the frame buffer. 2.2 GL state. The GL maintains considerable state. This document enumerates each state variable and describes how each variable can be changed. For purposes of discussion, state variables are categorized somewhat arbitrarily by their function. Although we describe the operations that the GL performs on the frame buffer is not a part of GL state. We distinguish two types of state. The first type of state, called GL server state, resides in the GL server. The majority of GL state falls into this category. The second type of state, called GL client state, resides in the GL client, unless version 2.0.25, November 2, 2010. 2.3. GL command syntax 9. Otherwise specified. All state referred to in this document as GL server state, GL client state is specifically identified. Each instance of a GL context implies one Complete set of GL server state. Each connection from a client to a server implies a set of both GL client state and GL server state. While an implementation of the GL may be hardware dependent, this discus Xeon is independent of the specific hardware on which a GL is implemented. We are, therefore, concerned with the state of graphics hardware only when it corresponds precisely to GL state. 2.2.1 Shared Object State. It is possible for groups of contexts to share certain state. Enabling such sharing between contexts is done through Windows System Binding APIs such as those described in section 1.6.1. These APIs are responsible for creation and management of contexts, and not discussed further here. More detailed discussion of the behavior of shared objects is included in Appendix C except as defined in this appendix. All state in a context is specific to that context only. 2.3 GL Command Syntax. GL commands are functions, are procedures. Various groups of commands perform the same operation but differ in how arguments are supplied to them. To conveniently accommodate this variation, we adopt a notation for describing commands and their arguments. GL commands are formed from a name followed, depending on the particular command, by up to 4 characters. The first character indicates the number of values of the indicated type that must be presented to the command. The second character, or character pair, indicates the specific type of the arguments: 32-bit integer, 32-bit fixed point, or single precision floating point. The final character, if present, is V, indicating that the command takes a pointer to an array, a vector of values rather than a series of individual arguments. 2 specific examples: void uniform 4f int location, float v0, float v1, float v2, float v3, and void get float venom value, float data. Version 2.0.25, November 2, 2010. 2.3 GL Command Syntax 10. Letter. Corresponding GL type. INT. F float. Table 2.1. Correspondence of command, suffix letters to GL argument types. Refer to Table 2.2 for definitions of the GL types. These examples show the ANSIC declarations for these commands. In general, a command declaration has the form 1. Retype name.
1234.
FFV. Args. targ1, targn, args. Retype is the return type of the function. The braces enclose a series of char actors or character pairs, of which one is selected, indicates no character. The arguments enclosed in brackets args and args may or may not be present. The n arguments arg1 through argn have type T, which corresponds to one of the typed letters or letter pairs as indicated in Table 2.1. If there are no letters, then the argument's type is given explicitly. If the final character is not V, then n is given by the digit 1, 2, 3, or 4. If there is no digit, then the number of arguments is fixed. If the final character is V, then only arg1 is present and it is an array of n values of the indicated type. For example, void uniform 1234, if int location, t value, indicates the 8 declarations. Void uniform 1i int location, int value. Void uniform 1f int location, float value. Void uniform 2i int location, int v0, int v1. Void uniform 2f int location, float v0, float v1. Void uniform 3i int location, int v0, int v1, int v2. Void uniform 3f int location, float v1, float v2, float v2. Void uniform 4i int location, int v0, int v1, int v2, int v3. 1. The declarations shown in this document apply to ANSIC languages, such as C++ and Ada, that allow passing of argument type information, admit simpler declarations and fewer entry points. Version 2.0.25, November 2, 2010. 2.4. Basic GL Operation 11. Void uniform 4f int location, float v0, float v1, float v2, float v3. Arguments whose type is fixed, i not indicated by a suffix on the command, are of one of the 13 types, or pointers to one of these summarized in Table 2.2. The mapping of GL data types to data types of a specific language binding are part of the language binding definition and may be platform dependent. Type conversion and type promotion behavior when mixing actual and formal arguments of different data types are specific to the language binding and platform. For example, the C language includes automatic conversion between integer and floating point data types, but does not include automatic conversion between the int n, fixed, or float n fixed GL types since the fixed data type is not a distinct built-in type. Regardless of language binding, the enum type converts to fixed point without scaling, and integer types are converted to fixed point by multiplying by 216. 2.4 Basic GL operation. Figure 2.1 shows a schematic diagram of the GL. Commands enter the GL on the left. Some commands specify geometric objects to be drawn, while others control how the objects are handled by the various stages. The first stage operates on geometric primitives described by vertices, points, line segments, and triangles. In this stage, vertices are transformed and lit and primitives are clipped to a viewing volume in preparation for the next stage, rasterization. The rasterizer produces a series of frame buffer addresses and values, using a two-dimensional description of a point, line segment, or triangle. Each fragment so produced is fed to the next stage, that performs operations on individual fragments before they finally alter the frame buffer. These operations include conditional updates into the frame buffer based on incoming and previously stored depth values, to effect depth buffering, blending of incoming fragment colors with stored colors, and other operations on fragment values, such as masking, see chap. Ter4. Values may also be read back from the frame buffer. These transfers may include some type of decoding or encoding. This ordering is meant only as a tool for describing the GL, not as a strict rule of how the GL is implemented, and we present it only as a means to organize the various operations of the GL. Version 2.0.25, November 2, 2010. 2.4. Basic GL Operation 12. GL Type. Minimum bit width. Description. Boolean. 1 Boolean. Byte. 8 signed binary integer. UByte. 8 unsigned binary integer. Char. 8 characters making up strings. Short. 16. Signed 2's complement binary integer. Short. 16. Unsigned binary integer. Int. 32. Signed 2's complement binary integer. UINT. 32. Unsigned binary integer. Fixed. 32. Signed 2's complement 16.16 scaled integer. SIZI. 32. Non-negative binary integer size. Enum. 32. Enumerated binary integer value. Int per. Terbits. Signed 2's complement binary integer. SIZIPTER. Terbits. Non-negative binary integer size. Bitfield. 32. Bitfield. Float. 32. Floating point value. Clamp. 32. Floating point value clamp 2. 0, 1. Table 2.2. GL data types. GL types are not C types. Thus, for example, GL type int is referred to as glint outside this document, and is not necessarily equivalent to the C type int. An implementation may use more bits than the number indicated in the table to represent a GL type. Correct interpretation of integer values outside the minimum range is not required, however. Terbits is the number of bits required to represent a pointer type. In other words, types intr and SIZIPTER must be sufficiently large as to store any address. Version 2.0.25, November 2, 2010. 2.4. Basic GL Operation 13. Per. Vertex operations. Primitive. Assembly. Rasterization. Per fragment. Operations. Frame buffer. Texture. Memory. Pixel. Operations. Figure 2.1. Block diagram of the GL. Version 2.0.25, November 2, 2010. 2.5. GL errors 14. 2.5 GL errors. The GL detects only a subset of those conditions that could be considered errors. This is because in many cases error checking would adversely impact the performance of an error-free program. The command, enum get error void, is used to obtain error information. Each detectable error is assigned a numeric code. When an error is detected, a flag is set and the code is recorded. Further, errors, if they occur, do not affect this recorded code. When get error is called, the code is returned and the flag is cleared, so that a further error will again record its code. If a call to get error returns no error, then there has been no detectable error since the last call to get error, or since the GL was initialized. To allow for distributed implementations, there may be several flag code pairs. In this case, after a call to get error returns a value other than no error, each subsequent call returns the non-zero code of a distinct flag code pair, in unspecified order until all non-no error codes have been returned. When there are no more non-no error codes, all flags are reset. This scheme requires some positive number of pairs of a flag bit and an integer. The initial state of all flags is cleared, and the initial value of all codes is no error. Table 2.3 summarizes GL errors. Currently, when an error flag is set, results of GL operation are undefined only if out of memory has occurred. In other cases, the command generating the error is ignored so that it has no effect on GL state or frame buffer contents. If the generating command returns a value, it returns 0. If the generating command modifies values through a pointer argument, no change is made to these values. These error semantics apply only to GL errors, not to system errors such as memory access errors. Extensions may change behavior that would otherwise generate errors in an unextended GL implementation. Several error generation conditions are implicit in the description of every GL command, if a command that requires an enumerated value is passed a symbolic constant that is not one of those specified as allowable for that command, the error or invalid enum error is generated. This is the case even if the argument is a pointer to a symbolic constant if the value pointed to is not allowable for the given command, if a negative number is provided where an argument of type SYSI is specified, the error invalid value is generated. Version 2.0.25, November 2, 2010. 2.6, Primitives and Vertices 15. Error. Description. Offending command ignored. Invalid enum. Enum argument out of range. Yes. Invalid frame buffer operation. Frame buffer is incomplete. Yes. Invalid value. Numeric argument out of range. Yes. Invalid operation. Operation illegal in current state. Yes. Out of memory. Not enough memory left to eggs. Q command. Unknown. Table 2.3. Summary of GL errors. If memory is exhausted as a side effect of the execution of a command, the error out of memory may be generated. Otherwise, errors are generated only for conditions that are explicitly described in this specification. 2.6 Primitives and vertices. In the GL, geometric objects are drawn by specifying a series of generic attribute sets using vertex arrays. See section 2.8. There are 7 geometric objects that are drawn this way: points, connected line segments, line strips, line segment loops, separated line segments, triangle strips, triangle fans, and separated triangles. Each vertex is specified with multiple generic vertex attributes. Each attribute is specified with 1, 2, 3, or 4 scalar values. Generic vertex attributes can be accessed from within vertex shaders, section 2.10, and used to compute values for consumption by later processing stages. The methods by which generic attributes are sent to the GL, as well as how attributes are used by vertex shaders to generate vertices mapped to the two-dimensional screen, are discussed later. Before vertex shader execution, the state required by a vertex is its multiple generic vertex attribute sets. After vertex shader execution, the state required by a process vertex is its screen space coordinates and any varying outputs written by the vertex shader. Figure 2.2 shows the sequence of operations that builds a primitive point, line, segment, or triangle from a sequence of vertices. After a primitive is formed, it is clipped to a viewing volume. This may alter the primitive by altering vertex coordinates and varying outputs. In the case of line and triangle primitives, clipping. Version 2.0.25, November 2, 2010. 2.6, Primitives and Vertices 16. Coordinates. Vertex shader. Execution. Shaded. Vertices. Point. Line segment or triangle. Primitive. Assembly. Point culling. Line segment or triangle. Clipping. Rasterization. Varying. Outputs. Generic. Vertex attributes. Primitive type. From draw arrays or draw elements mode. Figure 2.2 Vertex processing and primitive assembly. Version 2.0.25, November 2, 2010. 2.6, Primitives and Vertices 17. May insert new vertices into the primitive. The vertices defining a primitive to be rasterized have varying outputs associated with them. 2.6.1 Primitive types. A sequence of vertices is passed to the GL using the commands draw arrays or draw elements. See section 2.8. There is no limit to the number of vertices that may be specified, other than the size of the vertex arrays. The mode parameter of these commands determines the type of primitives to be drawn using these coordinate sets. the types, and the corresponding mode. Parameters are points. A series of individual points may be specified with mode points. Each vertex defines a separate point. Line strips. A series of one or more connected line segments may be specified. With mode line strip, at least two vertices must be provided. In this case, the first vertex specifies the first segment's start point, while the second vertex specifies the first segment's endpoint and the second segment's start point. In general, the if vertex for I1 specifies the beginning of the ith segment and the end of the negative first. The last vertex specifies the end of the last segment. If only one vertex is specified, then no primitive is generated. The required state consists of the processed vertex produced from the preceding vertex that was passed, so that a line segment can be generated from it to the current vertex, and a Boolean flag indicating if the current vertex is the first vertex. Line loops. Line loops may be specified with mode line loop. Loops are the same as line strips except that a final segment is added from the final specified vertex to the first vertex. The required state consists of the processed first vertex, in addition to the state required for line strips. Separate lines. Individual line segments, each specified by a pair of vertices, may be specified with mode lines. The first two vertices passed define the first segment, with subsequent pairs of vertices each defining one more segment. If the number of specified vertices is odd, then the last one is ignored. The required state is the same as for line strips, but it is used differently. A processed vertex holding the first endpoint of the current segment, and a Boolean flag indicating whether the current vertex is odd or even. A segment start or end. Triangle strips. A triangle strip is a series of triangles connected along shared edges specified by giving a series of defining vertices with mode triangle. Strip. In this case, the first three vertices define the first triangle, and their order is significant. Each subsequent vertex defines a new triangle using that point along. Version 2.0.25, November 2, 2010.